fracture pattern refers to the arrangement or distribution of fractures or cracks in a material such as rock or bone. It is the result of the forces or stresses that have been applied to the material, causing it to break or fracture. Fracture patterns can provide important information about the type and intensity of the forces that cause the fracture, as well as the properties and behavior of the material itself. For example, a material that is strong and brittle, such as some types of ceramics, may exhibit a different fracture pattern than a material that is more ductile, such as some metals. The pattern of fractures can also be used to enter the direction and magnitude of the forces that cause them. For instance, if the fractures are all oriented in a particular direction, it may suggest that the forces were applied in that direction. There are many different types of fracture patterns, including radial, concentric, spiral, and oblique fractures. Each type of fracture pattern has its own unique characteristics and can be indicative of different types of stresses or forces.
Broken or shattered glass found at a crime scene is an important piece of forensic evidence. The different types of glass that are often found, such as glass from window, lamp, headlights, or bottles, each have unique properties that can be measured and compared. When glass is shattered by a forceful impact, it scatters for distances up to 9 feet or so, and can be easily become lodged in a suspect's shoes, clothing, or hair. If a window or glass object is broken or shattered by a projectile, such as bullet, the breakage pattern can be analyzed to possibly determine the angle of trajectory of the projectile, or shedding more light on a crime, such as where the suspect was when the gun was fired.
The forms two types of fractures, radial fractures and concentric fractures. First is radial fractures. When glass breaks, fractures pattern form on the surface. Breaks called primary radial fractures are produced. These fractures start at the point of impact and radiate like spokes on a wheel outward from there. Radial fractures form on the sides and opposite point of impact. Second is concentric fractures. Secondary fractures may also form. These fractures takes the form of concentric circles around the point of impact. Concentric circles are circles that have the same center. Concentric circles form on the same sides of the glass as the point of impact.
Going to explain the force applied to a flat glass. When force is applied on any surface of glass, it bends, but since the elasticity of glass is limited, ultimately, it gets fractured after the threshold force application. An investigator often has to decide whether a pane of glass was broken from outside or from inside, whether it was broken with a bullet or with a blunt object. Impact causes a pane of glass to bulge. Since opposite the impact will stretch more and rupture first, radial cracks are rapidly propagated in short segments from the point of impact, and elasticity permits bending until radial cracks from on the opposite side of the force continued force place tension on the front surface, forming the radial and concentric cracks.
Primary radial fractures. When glass breaks, fracture patterns form on the surface. The breaks, called primary radial fractures, are produced. These fractures start at the point of impact and radiate, like spokes on a wheel, outward from there. Radial fractures form on the side opposite the point of impact.
Concentric secondary fractures. Secondary fractures may also form. These fractures take the form of concentric circles around the point of impact. Concentric circles are circles that have the same center. Concentric circles form on the same side of the glass as the point of impact.
3-hour rule. The 3-hour rule states radial fractures make right angles to the rear. By examining the radial fractures of the direction in which they form a right angle, the rear side of the pane of glass opposite the side the force was applied can be determined.
So as you can see, when the projectile hits a glass surface, the glass bends and energy dissipating from the point of impact causes radial fractures to occur on the side of the glass opposite the point of impact. Also, the stress marks on the edges of every radial fractures conform in a specific way which will show the direction of impact. So to determine where is the first and second penetration this is the first penetration wherein a lot of radial fractures as you can see in this glass. Also second penetration this. So to determine where is the second penetration is as you can see in the radial fracture of second penetration stop here, and this is the conchoidal fractures. So there's a slope. So this is the objective entrance and the exit pattern. The waves of energy from the projectile reverberate from the point of impact, causing the glass to fracture in a cone shape. However, the side of the glass which has stress marks which parallel to the surface of the side which sustain the impact. So if you can see closer in these glass fractures, the result is a small entrance hole and a large exit hole in the glass. In addition, the surrounding of the hole is made by a projectile. There will be concentric rings known as concentric fractures.